everything that we've been talking about up until now, we've made the assumption from the beginning that we have single-phase liquid reservoirs, such as oil reservoirs that are undersaturated, oil above the bubble point. We're going to want to make this work for gas reservoirs also. So the discussions that we've had so far are going to require, and the equations that we've developed are going to require some modifications to make them work for gas reservoirs. And I want to talk about what some of those modifications are. Most important thing to remember when we're talking about gas properties as opposed to oil properties is that gas properties are going to vary significantly with pressure. And gas compressibility is much, much higher than oil compressibility or liquid compressibility in general. Okay? A gas basically expands to fill its container. And so its properties are significantly different and have a different behavior with pressure and time than oil properties do. In some sense, oil properties are much easier to manage with the math and the analytics than gas properties are, because gas properties are very dynamic and nonlinear. But understanding how gas depletion works is going to be just as important for running RTA, because we want to analyze gas reservoirs with this. And so we need to understand how to do that. So the properties that we have particular interest in are the formation volume factor, the compressibility, and to a lesser extent the viscosity. We need to be able to handle these in some way. So first of all, I want to talk about what the problem is, why these are going to cause us a problem, and then we'll talk about how we can correct for them. So what you're looking at here is the pseudo steady state equation for oil written out in full. Okay? The term that's circled over here, this full term is the B pseudo steady state. So this is the inverse or reciprocal productivity index. And then the term up here is the depletion term. So this is where the material balance comes in. This is where the steady state inflow comes in. And gas properties are going to make an appearance in both of those terms in different ways. Okay? So let's talk about the reservoir flow term first of all. You'll notice that there is a B and a mu in there. And the B is the formation volume factor. The mu is the viscosity. Those things are going to influence the steady state inflow term. And in the case of an oil reservoir, we can assume that those are pretty much constant without too much problem, okay, above the bubble point. When we get into a situation with gas, the gas formation volume factor and viscosity are highly nonlinear. They change very rapidly. So we're going to need to have some sort of correction there. On the depletion side of things, you'll notice that there's a compressibility term in there. Gas compressibility is not constant. And so we can't just assume that there's constant. What we're doing here with oil is the assumption is that we had this constant compressibility. And we can't make that assumption for gas. In fact, if you look at the equations for gas, compressibility is fairly well approximated by 1 over pressure. Okay? Which is very, very different than the situation we have for oil. For oil, we effectively assume it's constant. For gas, we have compressibility that expands. The compressible energy of the reservoir, of the gas in the reservoir, expands significantly as pressure depletes. So these two are both going to present separate problems that we need corrections for. So first of all, I want to talk about the inflow correction. And this goes right back to Darcy's law. If you have Darcy's law for a liquid, basically we have a proportionality between the pressure loss and the flow rate. And this is simply not the case for gas. Okay? For gas, the viscosity and the Z factor have a significant influence on the pressure loss or the drawdown in the reservoir. And they vary significantly with pressure. So what ends up happening is that there's more of a pressure loss for a given flow rate in a gas reservoir than just the delta P. Okay? And we solve that problem with pseudo pressure. To give a little more of a practical perspective on this, one only needs to remember the IPR curve for gas. So an IPR relationship for gas is usually done with flowing pressure plotted against production rate. So we have production rate on the bottom, flowing pressure on the side. We all know that this is not a linear relationship. Okay? There's a well-known equation, the Rollins-Shellhart equation. And the Rollins-Shellhart equation essentially says that flow rate is equal to some constant multiplied by P bar squared minus P flowing squared, and then raised to the power of n. And this equation is used extensively for pipeline engineering and gas deliverability engineering. What this illustrates is the observation, because this is an empirical equation, but it illustrates the observation that the production rate that you see in a gas reservoir is related not to the difference in pressures, but to the difference in squares of the pressures. Okay? And this is partly due to the fact that viscosity and formation volume factor vary so much in that drawdown region in the well. So in a practical sense, this problem is solved by using P squared. Okay? And we could use that as a solution to this. Instead of using pressure, use P squared. And that's not a bad approximation. And a lot of people use that approximation. But it turns out there's a better approximation. In fact, to be rigorous about it, we want to use pseudo pressure. P squared is a pretty good approximation as long as you have as long as the pressures are quite low. When the pressures get up into the higher regions, it doesn't work as well. So it has a limited range of application. So what we prefer to use instead is pseudo pressure. And pseudo pressure will solve this problem for any range of pressure and temperature. And it's an exact solution. So effectively what we do is if you provide the gas composition, pressure and temperature, I can look up in a table or use a equation of state to determine a pseudo pressure and deliver that back to you. Okay, so it's a direct transformation. As soon as you've provided the pressure and the gas composition, I can give you the pseudo pressure. So this is an easy one to do. And with the software, what we can do is if there's, because engineers and people working with pressures and rates typically don't like to look at pseudo pressures. It's a little bit of an abstract thing. You'd rather see the real pressures. That's what you're used to seeing. So what we can do is internally do pseudo pressures, but always display it in terms of pressure. And one of the ways you can do that is use a nonlinear scale that plots the pressure instead of the pseudo pressure. So there's all kinds of tricks that we invoke for doing that. But this is an easy correction to make. And pseudo pressure has been used in the well test literature for many years. So it's not a new concept. This one's a little more tricky. This is the depletion part of things. So when we talked about the pseudo pressure correction, we're really interested in what's happening near the well, in the drawdown cone, if you want to call it that. But also what has a huge impact is what happens everywhere in the reservoir. And that's in the depletion. Okay? Because if you think about it, in the depletion, when the reservoir is depleting, the reservoir pressure is dropping everywhere in the reservoir. So we need to have something that's going to correct for declining reservoir pressure. And pseudo pressure is not going to be enough on its own. So again, I drew this on the board earlier. Gas compressibility is roughly equal to the inverse of pressure. And so when we plot it, it's going to have this very strong nonlinear shape to it. At very high pressures, gas compressibility is reasonably well behaved. But when we get into low pressures, it expands and sort of goes through the roof and increases quite dramatically. So we need a way of handling that. We can't assume that compressibility is constant, which the pseudo-steady state equation requires, in this M pseudo-steady state, requires us to put in a C value. What would we do for gas? We wouldn't be able to put in a fixed C value because it's changing. So what we do with gas reservoirs is we use a concept called pseudo-time. This concept was first invented by Ram Agarwal way back a few years ago. And it actually was defined not at all for this purpose, but for well test interpretation, for buildups. It was defined to handle changing storage in the wellbore when we first start the buildup. Okay, because we have the same problem there. We have this concept that the pressure is changing in the wellbore, and therefore the compressibility of the gas is changing significantly. Later on, in the mid-90s, Frame and Wattenberger, who are at Texas A&M, developed a similar pseudo-time function, but it was designed for the whole reservoir, the reservoir as a whole. Okay? So it wasn't for buildups, it was for long-term drawdowns, and the volume that we're interested in is the volume of the entire reservoir. So this definition is really the same as the original Agarwal definition, but it's been enhanced to calculate the or to calculate the gas properties at average reservoir pressure. Okay? So this equation is fairly straightforward, but very difficult to calculate. One of the reasons it's difficult is because we need to know mu and c at average reservoir pressure, but we don't know what average reservoir pressure is. That's one of the things we're trying to figure out. So this becomes a little bit of a problem right away. The other issue with this is that it's not a direct calculation. You can't just go and look up, if I gave you the if I gave you the gas composition and temperature, you wouldn't just be able to go look up pseudotime in a table. Pseudotime is inherently tied to the well production history. So it's a two-step transformation, right? I need to know the well history and take all the times and convert them to pseudotimes. The other thing I need to do is I need to do this iteratively, because I don't know the reservoir pressure to start with, so I have to iterate to get there. Not easy to do if you're doing it by hand. Luckily, we have the software which can make it much easier to do this. And I'm going to switch back to my other example of boundary-dominated flow. And what you're going to see once we get back to this example is that there's this dynamic effect. Whenever we're looking at a gas reservoir and we're analyzing the data with the software, you're going to see this dynamic effect. And the data sort of moves. You can also see it on the flowing material balance plot. The data has a dynamic effect. Okay? And what's going on there is that the pseudotime is constantly being recalculated on the fly, because the positions of the data points are dependent upon your estimate of original gas in place. And therefore, it needs to be constantly being recalculated. So there's always this dynamic effect for gas. The pseudo pressures are behind the scenes. They're being done directly. There's no iterations there. But for pseudotimes, we require iterations to make it work. So once we have made the conversions of pseudo pressure and pseudo time, effectively we can take the oil pseudo steady state equation and make it applicable to gas. Why do we want to do that? Well, the whole purpose, if you recall, of having this flowing material balance equation or the pseudo steady state equation is that we can take the slope of it and determine the oil in place or the gas in place, right? So if you remember, we did this for oil. It was delta P over Q versus NP over Q. And we were able to get a straight line. There's that key term again, straight line. If it's not a straight line, it's not going to help us. So if we did this same thing for gas without using the pseudo variables, I can tell you, because I've done this in Excel before, is you'll get some sort of weird wiggly line like that. And what part of the slope do you take there? Do you take the slope here? Do you take it here? Do you take it here? You're going to get 7 different answers. So what's really important to us is not the plot itself, but it's the fact that it makes a straight line. And when we do this for a liquid case, we get a straight line when we use pressure, and for constant rate, this would be time. To get the straight line back for gas reservoirs, we have to use pseudo pressure instead of pressure, and we have to use pseudo time instead of time. If we do that, so we make that pseudo pressure, and we make this pseudo time, TA stands for pseudo time. Then we get our straight line back, and we can use this straight line to get the original gas in place. Okay? So what the pseudo variables do is they take gas and they mold it in to make it look like a liquid, as far as that plot is concerned. And so that's the whole purpose of doing that. So it's sort of an ingenious method of tricking the variables, or taking the complexity out of the equation and putting it into these special variables to make it look like it's a liquid, because we know how to analyze a liquid already. Right? We can get the straight line and go forward from there, and makes it look the same. Of course, we can make this work for a variable rate case also. The variable rate case is no different than that of oil. We use material balance time for gas in the same way that we use it for oil. It's just that we have to make sure that we're doing the pseudo time as well. So if we can keep that all in mind, we'll get the same quality of answers for gas as we do for oil. So at the end of the day, we have this overall pseudotime function that we define. The T, the C, and A. The C stands for the material balance time part. So that's the superposition that's been done on the time, which is cumulative production divided by flow rate. And then we've got the A, which is the pseudotime part. The pseudotime part accounts for the changing gas properties with time. And everywhere in the program where we're doing production analysis on the type curves or on the flowing material balance, anywhere where there's a time function that's in there, it's always material balance pseudo time if it's gas. If it's oil, then it's just going to be material balance time. And one final thing to go along with this, there's no reason that you would have to stop there. You can make this more rigorous for certain cases. Let me give you an example. Let's say you had a water drive and you had water influx coming in. Well, that's going to impact your pseudo time as well. Effectively, what happens with the pseudo time is it becomes unto itself the gas material balance. And anything that has to do with the energy in the reservoir changing through time, or all the terms that go into the energy, are basically rolled up into this pseudo time function, which makes it very convenient because I can account for lots of non-idealities in the system. Okay, and I mentioned one of them. One of them is a water influx case. Another one that we use this for a lot is overpressured reservoirs. In overpressured reservoirs, I have to include the effect of the formation compressibility. So that gets rolled into the pseudo time function as well. Okay? In fact, anything that has to do with an energy term in the reservoir can be included in this pseudo time function. So we can end up having a fairly complex and sophisticated pseudo time function that contains all of these different things if we want to include them. And the software will allow you to include those things if you want to. In many cases, it doesn't make a difference. For example, if it's a normally pressured reservoir and you don't use CF or you do use CF, it's really not going to make any difference. But if it's an overpressured reservoir, it may make a significant difference, which one of those you use.